Element 115, Moscovium. A synthetic, super-heavy element first synthesized in 2003 by Russian and American scientists at the Joint Institute for Nuclear Research. With an atomic number of 115, Moscovium exists only fleetingly. Its most stable isotope, Mc-290, decaying in under a second. A highly unstable post-transition metal, Moscovium belongs to the expanding frontiers of nuclear science. It was named after the Moscow region of Russia and officially recognized by the IUPAC in 2016. But long before its official discovery, element 115 was already legendary. In 1989, Bob Lazar, a controversial figure in UFO research, claimed that a stable isotope of element 115 powered extraterrestrial spacecraft at a secret facility near Area 51. According to Lazar, this reactor technology manipulated gravity itself, enabling faster-than-light propulsion. Mainstream science rejects these claims. No known isotope of Moscovium exhibits stability, and no evidence supports its use in exotic propulsion. Yet, the mystery lingers. Some nuclear physicists propose the existence of longer-lived super-heavy elements, a theoretical island of stability, where certain isotopes could resist decay for extended periods. If a stable version of element 115 were found, its implications could be revolutionary, from exotic propulsion to entirely new forms of energy generation. But does such an element truly exist, or is it purely science fiction?
For centuries, humanity has dreamed of defying gravity. From mythological tales of flight to modern theories of warp drives and faster-than-light travel, the pursuit of gravitational control remains one of the greatest challenges in physics. Among the many speculative technologies proposed, one stands out, both controversial and intriguing: element 115. In 1989, physicist Bob Lazar claimed that a stable isotope of element 115 was the key to an exotic propulsion system used in extraterrestrial spacecraft. According to Lazar, this element could generate its own gravitational field, distort space-time, and enable faster-than-light travel. At the time, element 115 was unknown to science. But in 2003, Russian and American researchers successfully synthesized Moscovium, element 115's official name. However, this version was highly unstable, decaying in just milliseconds. Could there exist a yet undiscovered isotope of element 115 with the properties Lazar described? And if so, could it redefine the laws of physics? Some physicists believe that within the island of stability, a longer-lived isotope of element 115 could exist, one that resists decay long enough to be studied, potentially revealing exotic nuclear and gravitational properties. Could element 115 be the key to anti-gravity propulsion, or is it just another unsolved mystery? At the extreme limits of atomic structure, where nuclear forces struggle against Coulomb repulsion, lie the super-heavy elements. Among them, element 115, Moscovium, occupies a unique position in the transactinide series. Unlike lighter elements, whose stability is dictated by the strong nuclear force, super-heavy elements exist in a delicate balance between nuclear binding energy and proton-neutron ratios. The fundamental equation governing nuclear binding energy is Eb equals Zmp plus Nmn nucleus C superscript 2, where Z is the number of protons, 115 for Moscovium. N is the number of neutrons, defined as N equals A, Z, where A is the atomic mass number. Mp and Mn are the masses of protons and neutrons, respectively. Nucleus is the measured nuclear mass. C is the speed of light. This equation reveals how nuclear mass defects translate into binding energy, a key factor in determining whether an isotope is stable or decays in mere milliseconds. To date, 4 isotopes of Moscovium have been synthesized, with Mc-290 exhibiting the longest half-life at 650 milliseconds. Yet, theoretical models predict that an isotope with N is almost equal to 184 neutrons could reside within the island of stability, a region where quantum shell effects enhance nuclear longevity. If such an isotope exists, it could defy conventional decay rates, opening the door to exotic nuclear properties, perhaps even gravitational interactions beyond the standard model. Could the search for stable superheavy elements lead us to a new frontier in physics?
In nuclear physics, stability is dictated by magic numbers, specific proton and neutron counts where nuclear shells are completely filled, increasing binding energy and reducing decay rates. These magic numbers suggest that a yet undiscovered neutron-rich isotope of Moscovium, MC 299, with 184 neutrons, could be far more stable than its known counterparts. To date, all synthesized isotopes of Moscovium have decayed within milliseconds. However, if MC 299 exists, its half-life could be seconds, minutes, or even longer, making it experimentally accessible for the first time. The semi-empirical mass formula, SEMF, predicts nuclear stability by balancing nuclear volume energy, surface tension, Coulomb repulsion, and asymmetry effects. For a hypothetical MC 299 isotope, Coulomb repulsion must be offset by quantum shell effects. Otherwise, the nucleus would decay instantly. But how could such an isotope be produced? Possible production methods include heavy ion fusion, bombarding lead or bismuth with neutron-rich projectiles to create MC 299, neutron star matter bombardment, extracting material from neutron stars to enrich Moscovium nuclei, and particle accelerator neutron enrichment, using controlled high neutron flux environments to force neutron absorption. If these methods succeed, synthetic isotopes of element 115 could be stable for seconds, minutes, or potentially much longer, unlocking entirely new frontiers in nuclear physics and exotic energy research. Could MC 299 be the breakthrough that leads us to the next era of advanced propulsion and energy systems?
Beyond conventional nuclear physics, advanced stabilization techniques may hold the key to extending the lifetime of element 115 isotopes. One speculative approach involves using intense electromagnetic fields to suppress nuclear decay mechanisms. This relies on high magnetic field stabilization, reducing alpha decay probability and quantum coherence effects, extending nuclear lifetimes through wave function manipulation. The probability of alpha decay follows a quantum mechanical tunneling process, T equals E caret minus 2g, where g is the game-off factor, g equals 2z superscript 2 forward slash v. A strong external magnetic field exceeding 10 superscript 1 superscript 2 Gauss could alter the nuclear wave function, reducing tunneling probability and increasing the isotope's half-life. Applications of magnetic containment include plasma confinement chambers, suspending element 115 in a rotating electromagnetic field to prevent immediate decay, and superconducting lattice embedding, incorporating Moscovium atoms into a superconducting structure to exploit quantum stabilization. While speculative, quantum suppression of nuclear decay has been observed in electron capture modulation experiments, suggesting that similar techniques could influence superheavy elements. More extreme hypotheses suggest that exotic matter or extradimensional interactions could fundamentally modify element 115's nuclear decay properties. The exotic matter coupling hypothesis posits that if negative energy fields exist, through vacuum polarization or Casimir effect engineering, they could alter nuclear stability. A controlled exotic vacuum state might suppress alpha decay, allowing element 115 to remain stable. If hidden spatial dimensions exist, as suggested by string theory and brane-world models, nuclear interactions may be influenced by extradimensional force effects. This concept can be modeled using a modified Yukawa potential, V R equals E caret MR slash R plus E caret M R underscore extra slash R underscore extra, where R underscore extra represents nuclear interactions extending beyond 3D space. If such effects exist, certain isotopes of element 115 could be stabilized by extradimensional interactions, modifying nuclear force strengths and reducing decay rates. Could these cutting-edge approaches unlock stable superheavy elements and lead to new physics beyond the standard model?
If a stable isotope of Moscovium MC 299 and equals 184 exists, it may exhibit unique quantum gravitational properties, potentially altering our understanding of space-time and propulsion. Two key mechanisms could drive gravitational anomalies in MC 299. Enhance nuclear binding energy, increasing the density of quantum vacuum fluctuations near the nucleus, and possible weak interactions with space-time curvature, leading to measurable gravitational distortions. The semi-empirical mass formula, SEMF, suggests that nuclear shell closures could reduce decay rates and modify how element 115 interacts with spacetime. Stable element 115 may function as a gravitational lens, bending spacetime around it. By controlling nuclear density fluctuations, a ship could create a localized gradient in spacetime curvature, enabling precise gravitational control. This would function similarly to frame dragging effects predicted by general relativity, where dense objects induce gravitational vortices. Neutron interferometry experiments could measure weak gravitational fields around high-density Moscovium samples. Muon decay rate changes within a Moscovium gravitational lens could serve as indirect evidence of quantum gravity interactions. If MC 299 exhibits space-time curvature properties, it would provide the first experimental foundation for an engineered gravity distortion field, a critical step toward controlled anti-gravity propulsion. A high neutron density isotope of element 115 might generate non-classical gravitational interactions due to high local mass energy density, increasing its gravitational potential, and anisotropic nuclear force fields, generating localized mass energy distortions in spacetime. The gravitational potential of a neutron-rich nucleus is given by phi_g equals G_nucleus /r, where increasing neutron number enhances local gravitational wells. If MC 299 forms a small artificial gravity well, it could enable controlled inertial modification, reducing effective mass during acceleration and directional acceleration without reaction mass, by modulating neutron distribution within the element 115 core. This could resemble Alcubierre-type metric engineering, where localized distortions in the metric tensor permit apparent superluminal travel. Cyclotron bombardment of neutron-rich Moscovium isotopes could detect gravitational anomalies. Precision accelerometry of neutron-loaded samples could determine whether local inertial mass changes. If neutron superloading can be controlled, it would provide a direct experimental pathway to creating artificial gravity distortions, a necessary step toward reactionless propulsion. Could MC 299 be the missing link between modern physics and a new era of space travel? If element 115 can be stabilized, it may allow for direct gravity wave manipulation using magnetic confinement and exotic vacuum interactions. Strong electromagnetic fields could suppress nuclear decay and alter element 115's wave function, enabling magnetic field suppression of alpha decay, leading to long-lived isotopes and interaction of confined nuclear states with external spacetime metric fluctuations. The modified quantum tunneling equation suggests T equals E caret minus 2G plus B underscore perp caret 2, where B underscore perp is the magnetic field component perpendicular to the nuclear dipole. Applying strong magnetic fields may alter decay probabilities, potentially unlocking stable Moscovium isotopes with gravitationally active properties. A magnetically confined Moscovium core could generate oscillating gravity wave emissions, creating a standing wave propulsion effect. This could enable direct gravity manipulation with minimal energy input, leveraging parametric resonances between nuclear states and space-time fluctuations. Superconducting Moscovium matrix experiments to test for decay suppression and LIGO scale detection arrays tuned for gravity wave oscillations from nuclear spin interactions could provide the first experimental foundation for gravity wave propulsion, offering a pathway toward field-based gravity control. A stable MC 299 isotope may interact with exotic vacuum states, modifying local quantum field densities and leading to negative energy effects. The energy density equation for Casimir interactions suggests ρ_vacuum equals C pi caret 2 / 240d to the power of 4, where d is the distance between interacting surfaces. If Moscovium's nuclear wave function interacts with exotic vacuum states, It could generate localized repulsive gravity fields, functioning as a gravity shielding effect, enabling frictionless propulsion by modifying vacuum energy densities. Vacuum energy perturbation tests using element 115 under extreme electromagnetic fields and detecting anomalous force effects in superconducting cavities containing stable Moscovium could provide the first experimental demonstration of vacuum-induced propulsion, taking gravity control from theory to reality. Could element 115 be the missing link between quantum gravity, negative energy fields, and the future of interstellar travel?
At the heart of the anti-gravity reactor lies a stabilized MC 299 core, a theoretical isotope of element 115 designed to sustain nuclear reactions and gravitational manipulation. To function as a gravity-altering energy source, the MC 299 reactor must meet three key engineering challenges: increased nuclear stability, preventing rapid decay using neutron superloading, magnetic confinement, and vacuum field manipulation, high mass energy density, harnessing nuclear binding energy to generate localized gravity wells, energy harvesting for propulsion, converting nuclear reaction energy into gravitational field modulation, allowing for reactionless thrust. The MC 299 core is engineered as a spherical or cylindrical lattice composed of stabilized isotopes, surrounded by a high-energy magnetic containment system. To ensure stability and field shaping, the reactor employs toroidal magnetic fields to trap and stabilize the isotopes, superconducting coils to generate intense, controlled magnetic fields, and cryogenic cooling systems to maintain the superconducting state and optimize energy efficiency. These elements work together to control the isotopic reactions, reduce inertial mass, and stabilize MC 299 against rapid decay. To superload MC 299 with neutrons and maintain stability, neutron flux control systems precisely regulate neutron input using particle accelerators, generating high-energy neutrons and neutron injectors, ensuring a consistent reaction rate. By carefully tuning neutron absorption, the reactor can maintain a delicate balance between energy release and isotope longevity. As MC 299 undergoes nuclear reactions, whether fission, fusion, or neutron-induced interactions, the resulting energy is harvested and converted for propulsion. This energy may be released as gamma radiation, requiring shielding and conversion mechanisms, neutrino emissions, interacting weakly with matter, but potentially useful for exotic energy transfer, gravitational wave emissions, modulating space-time for direct propulsion effects. By controlling gravity wave emissions, the MC 299 reactor may serve as the foundation for reactionless propulsion, eliminating the need for conventional rocket thrust. Could this be the first step toward true interstellar travel, powered by the gravitational potential of element 115?
To achieve true anti-gravity propulsion, we must build a reactor core capable of stabilizing and harnessing the exotic properties of MC 299, an advanced isotope of element 115. The MC 299 anti-gravity reactor must meet three critical engineering challenges: withstand extreme conditions, efficiently convert nuclear energy, and ensure safety and stability. The reactor will use high-temperature superconductors, such as yttrium barium copper oxide, to generate the powerful magnetic fields needed to contain and stabilize MC 299 and operate efficiently at cryogenic temperatures, minimizing energy loss. Radiation shielding will include neutron shielding using borate, polyethylene, or graphite to absorb high-energy neutrons, and gamma shielding with lead or tungsten to block radiation emissions. A cryogenic cooling system will maintain superconductivity and dissipate excess heat. Once MC 299 is stabilized, its nuclear reactions will generate energy that can be harnessed through thermal to electrical conversion, electromagnetic field generation, and gravitational energy harvesting. At the core of anti-gravity propulsion is the ability to manipulate gravitational fields. The system will include a gravitational lens field to create localized gravitational wells, to bend spacetime, and field oscillators to use oscillating gravitational fields to generate thrust. The reactor will include automated radiation shielding, pressure and temperature regulation, and magnetic containment backup systems to ensure safety, efficiency, and scalability. To ensure scalability, the reactor will optimize energy extraction and allow modular designs for spacecraft of various sizes. Before deployment, the reactor must pass reactor core stability tests, gravitational wave detection, and energy output verification. By stabilizing element 115, manipulating gravitational fields, and harnessing vacuum energy, we could unlock reactionless propulsion, transforming interstellar travel. Could this be the next great breakthrough in advanced physics and space exploration?